The CPU doesn't follow your intentions, it follows paths. Every bug you've ever chased was a mismatch between the path you assumed and the state the CPU actually used. In this deep dive, we'll build a mental model you can reuse. Execution creates moments. Moments expose values, and values drive branches. First, a baseline. Execution is linear until control flow changes it. The CPU does not look ahead. It executes the current line, then the next line, in order. That sounds obvious. But most mistakes come from forgetting it under pressure. When you read code, you often compress steps. You jump to the conclusion. The CPU can't. It performs each read and write. So our tracing rule is, at every line, answer two questions. What values exist right now? And what will this line change? If you can't answer, you're not tracing, you're guessing. Now time. Time is not a variable you declare, but it's baked into execution. Every statement runs at a moment, and the moment determines which state is visible. Think of state as snapshots. After each statement, a new snapshot exists. Debugging is comparing your expected snapshot to the real one. That's why stepping in a debugger feels revealing. It forces you to respect moments. So when someone says that variable should be true, translate it to, by this moment, a write to true should have happened. That translation turns emotion into evidence. That's also why logs must include the moment and the value, not just the label. Two lines can both be correct, yet wrong together. Watch this. We check a flag before we set it. The check reads stale state, then we write too late. No compiler warning, no exception, just wrong behavior. This is a classic works locally, fails in prod pattern when concurrency or timing changes amplify the window. Your fix isn't magic, it's ordering. Make the write happen before the read, or redesign so the check doesn't depend on mutable state. The CPU is innocent. We gave it a bad sequence. The branch history illusion is where subtle bugs live. You'll see code that assumes the path is still true later. If axis is 10, the admin branch must have run, but axis could be overwritten, defaulted, or set by a different path earlier. The CPU doesn't carry your story forward. It carries only values. If you need history, model history. Store it, pass it, or compute it again. Otherwise, treat every later read as independent. It sees only the most recent write on the executed path. A control flow branch is simply the moment execution chooses one path over another. The CPU does not carry a tag like I came from else. It just continues with whatever state exists. Here's a tempting thought. If axis equals 10 later, that proves we went through the admin path. That's a story, not a guarantee. Axis could be overwritten by another method, reset by a constructor, defaulted, or set by a completely different condition earlier. The CPU doesn't protect your narrative. It only preserves values. So treat, how do we get here? As a state question, not a path question. If you need to know the path, store an explicit state like roll, or compute from trusted inputs at the moment you need it. If you feel unsure, that's normal. You're replacing a story with a trace. During the if, only one block runs. When the block ends, both paths rejoin the same next line. They don't merge histories. There's only the state produced, axis is 10 or 1. That's why bugs show up after branches. The next line reads a value without understanding its origin. Your job is to ensure both paths produce valid state, or handle state explicitly afterward. Branches end, state persists. Think of the next line as blind. It only sees the variable, not the journey. That's a dangerous silent bug. Unassigned variables. Consider a proof defaulting to false. Your release never happens and nobody notices until money is late. When you review code, scan for reads. If a variable is read before it's written, you're relying on a default. Silent bugs are the most expensive because they look like nothing happened. The bug isn't the if statement. It's the missed assignment before the if. The CPU is doing exactly what you told it to. Read approved? False, skip the block. That's why, but we never said it. It's not a defense. The system still behaved. The fixed patterns are simple, initializing the same scope as the decision. Pass the value in as a parameter. Or restructure so the decision is based on computed results rather than mutable fields. If the value matters, write it before the read. Treat missing initialization as a bug until proven otherwise. A return is a control flow branch with a hard edge. Everything below becomes unreachable. This is powerful for guard classes. Return early when invalid. It's also a common source of sometimes it doesn't save bugs. If process and save are below return, then any path that triggers a return deletes those operations. Draw the path that leads to the symptom and verify the path. When you scale a system, you don't just add lines, you add paths. More paths mean more combinations of state and time and more chances for a read to occur before the write. That's why simple feature changes can cause bizarre regressions. You change the path graph. The debugging move is consistent. Find the read that surprised you, then trace backward along the executed path to the last write that could influence it. If you can draw the path, you can predict the bug. Scaling is mostly adding branches. Every new condition, retry, guard, and fallback adds another path the system can take, and another set of states that can exist afterward. That's why mature codebases feel unpredictable. If you want stability, you reduce paths or you make the state produced by each path tightly controlled. The goal is not to be clever, it's to be traceable. Scaling is mostly adding branches, not adding lines. Good design reduces hidden mutable state, makes invariants explicit, and keeps decisions close to the data that drives them. It also makes illegal states unrepresentable where possible. Instead of a flag that can be stale, use a computed property or a validated enum. When you introduce a new branch, ask what state can exit this block, and are they all safe for the next line? If not, your design is incomplete, even if the code compiles. Here's a practical checklist you can use tomorrow. For any function, mark every write, every read, and every flow split. If else, loop conditions, returns, and throws. Then, for each read, ask which writes could possibly have happened before this read on the executed path. If the answer includes none, you're using defaults. If the answer includes a write in another branch, you're assuming history. If the answer includes a write later, you have an order bug. This is tracing as a method, not a mood.